Hey everyone. So in this video I like to define the inverse tangent function. And so let's do so by reminding ourselves first what y is equal to tangent of x can be interpreted as, or at least the outputs. How can we interpret the outputs of our tangent function? And so first off, just like our other trigonometric functions, sine and cosine, the inputs can be interpreted as angles. And the outputs of our tangent function, well, these take the y-coordinates on our circle and divide it by the x-coordinates on our circle. And these can be seen as the slope of our angle. This ratio can be seen as a slope. And so when we define y is equal to tangent inverse of x, well, an inverse function reverses the roles of the inputs and outputs of the original function. And so here, the input of our inverse function can be seen as a slope, and the outputs of our tangent inverse function, these can be seen as angles. And so if we take a look at a particular example like tangent inverse of 1, well, that input can be seen as a slope. We're looking for an angle with a slope of 1. And so what does a slope of 1 look like? Well, a slope of 1 is, any line with a slope of 1 goes up 1 and over 1. So we're looking from right to left, or left to right. And so here, one such angle that would do the job, that would fall on this line with a slope of 1, would be the angle pi over 4. Though notice if we look across this circle here to an angle of, what is this? This is 5 pi over 4. We also find another angle that lies on this line with a slope of 1. This is also an angle with a slope of 1. And there are many, many more, right? We can continue this process and go to all the coterminal angles to these two angles, right? Like 9 pi over 4, or here this would be 13 pi over 4 would be another angle. There's infinitely many angles which have a slope of 1. And so tangent inverse, it's meant to be a function. And so what should tangent inverse of 1 give us? Which one of these angles? Well, here, let's take a look at the graph of our tangent inverse function. Right, the graph of our tangent function. And so just like for our sine and cosine function, to define the inverse function, we define it as the inverse of some restriction of our original sine function and our cosine function. And so that's what we're going to need to do here. This tangent function does not pass the horizontal line test. It repeats the same outputs many, many times. And to define a tangent inverse function, we have to restrict our tangent function to a particular interval of input values, an interval of angles, so that it doesn't repeat itself, so that we don't get the same outputs. And so one part of our tangent function that doesn't repeat the same outputs is this part here, right in the middle, right? So here if I highlight this part right in the middle here, maybe I'll highlight it in blue. This part of our tangent function does not repeat itself. It passes the horizontal line test. It's 1 to 1 is another word for that. And so we can define an inverse function for this part of the tangent function. And so this part of the tangent function is from negative pi over 2 to pi over 2. Though tangent is undefined at these particular values of negative pi over 2 and pi over 2 themselves, so we can't include these values. Really, tangent inverse is only defined on the open interval from negative pi over 2 to pi over 2. In other words, excluding the boundary values. And so what this really means is that when we're evaluating our tangent inverse function, we're really just looking for an angle that has the slope of this input, in this case 1. We're only getting the angle between negative pi over 2 and pi over 2. In other words, our angle is specifically in this window here, from negative pi over 2 to pi over 2. And so here, the angles that I've written out that we're not going to consider for this tangent inverse function, 5 pi over 4, that's tossed out, 13 pi over 4, and 9 pi over 4, these are not going to be outputs of our tangent inverse function. They do have a slope of 1 when we compute the tangent value of these angles, but they're not going to be what we get from our inverse tangent function. We're going to get pi over 4. So let's evaluate our inverse tangent function at a few different values just to get a little more familiar with this function. So arctangent of 0, this is identical to inverse tangent of 0. So arctangent of 0 is saying that we have an angle with a slope of 0. What is this angle? But we're specifically looking for angles between negative pi over 2 and pi over 2. And so here, maybe let me start by drawing a line with a slope of 0. So here, angles with the slope of 0 land here and here. But arctangent is only going to give us back angles between negative pi over 2 and pi over 2. So here, arctangent is going to give us back specifically the angle that lies here on the right. But between negative pi over 2 and pi over 2, well, that's an angle of 0. Okay, so this is equal to 0 itself. Arctangent of 0 is 0. Now what about tangent inverse of negative 1? Well, here we're looking at a slope of negative 1. This represents a slope of negative 1. And we're asking what's an angle that has this slope of negative 1? But specifically, what angle between negative pi over 2 and pi over 2? Well, that's this angle here. Okay, so here, this is the angle. We saw that pi over 4 gave us an angle with a slope of 1, and negative pi over 4, this angle that's sort of sloped downwards, this has a slope of negative 1. So tangent inverse of negative 1 is going to give us negative pi over 4. So now let's take a look at tangent inverse of the square root of 3. So the square root of 3 feels a little bit less familiar and easy to work with than slopes of 0 and slopes of 1 and negative 1. But the square root of 3 appeared when we dealt with trigonometric functions involving a 30, 60, 90 triangle. Right, so here when we're looking at tangent inverse of the square root of 3, we should expect that a 30, 60, 90 triangle will sort of fit into this picture. And now tangent inverse, the inputs represent slopes. And the square root of 3, well, if that's going to be the slope of some line, I know that's a slope that's bigger than 1 because the square root of 3 is bigger than 1. Right, so if I imagine a slope of a line, the slope's slightly bigger than 1, and I'm expecting a 30, 60, 90 triangle to be in this picture, then this looks like it might be corresponding to an angle of pi over 3. And so let's check that. So theta is equal to pi over 3. I'm going to put a question mark here because I'm not certain that this is the right value of our inverse tangent function of square root of 3. But we can check this by taking tangent of pi over 3 and asking ourselves, does this give us the square root of 3? Then we'll know that the inverse tangent function should bring square root of 3 back to pi over 3. And so maybe I'll write this down below. So does tangent of pi over 3, does this equal the square root of 3? Well, tangent of pi over 3 is equal to sine of pi over 3 divided by cosine of pi over 3. And sine of pi over 3, that's the square root of 3 over 2. Cosine of pi over 3, that's 1/2. And so here when we multiply the top and the bottom by 2 to clear out the fractions, this becomes the square root of 3 over 1, or in other words, just the square root of 3. So tangent of pi over 3 is the square root of 3. And so inverse tangent of the square root of 3 is going to give us pi over 3. Because this is an angle that corresponds to the slope, and this angle falls between negative pi over 2 and pi over 2. It's in the window that's valid for our inverse tangent function. So all that to say that tangent inverse of the square root of 3, that's pi over 3. Now what about tangent inverse of cosine of 0? Well, here we have to just take this one step at a time and work our way from inside out. So tangent inverse of cosine of 0, well, what's cosine of 0? Cosine of 0 is, I'll use our unit circle here. Right, cosine takes the x-coordinate on the unit circle corresponding to our input angle. The input angle is 0 here. And so the x-coordinate at this point corresponding to an angle of 0, that's 1. Right? So this is cosine of 0 is 1. And so now tangent inverse, and maybe I should write this in green because it's the output of our cosine function, but it's going to be the input of our tangent inverse function, and the inputs of our tangent inverse function, these are now slopes. Okay, so here we're looking at tangent inverse of a slope of 1, and we saw in the previous example that a slope of 1 corresponded to an angle of pi over 4. So this might be a good time to bring up the domain and the range of our tangent inverse function. And so, earlier in the quarter we said that for our tangent function, y is equal to tangent of x, the domain was a set of all values we could plug into this function. And because tangent of x is the same as sine of x over cosine of x, and this is a fraction, really there are a few angles here that we can't plug into our tangent function because they lead to a denominator of 0. Right? Whenever cosine gives us a value of 0, that same angle is not going to be something we can plug into our tangent function and get a defined result for. And so really the domain of our tangent function, really almost everything works. It's all real numbers, except any angles that make cosine 0, and those are at the top points on our unit circle, the bottom points on our unit circle. We have an x value of 0 on our unit circle, cosine will be 0, and make the denominator here 0, making our tangent function undefined. So here those are the angles that correspond to the top points are pi over 2, or any coterminal angles, and 3 pi over 2 in any coterminal angles. And so this can be expressed as pi over 2 plus pi n. So that's the domain of our tangent function. And the range of our tangent function, well, these are all real numbers. We can get any slope output from a tangent function. We can draw any angle with any steepness, so the range of our tangent function is all real numbers. Now for our inverse tangent function, this inverse was only going to be the inverse of a restricted tangent function. And so this restricted tangent function we're looking at is really only going to have the domain of negative pi over 2 to pi over 2, a part of the graph that doesn't repeat itself. This is what the inverse tangent function is defined to be the inverse of. Tangent, but only on this window. So that's the domain of the function that tangent inverses the inverse of. And so what that means is that the domain of our tangent inverse function, well, this will be the range of the original tangent function. This is all real numbers, negative infinity to infinity. And the range, well, it's the domain of our tangent function that's restricted. So this is negative pi over 2 to pi over 2.